Hello everyone. Good morning to those of you in and around the Houston area. Good afternoon to some of you. I see some of you are in the Middle East and even farther afield here. So good evening to some of you also. And thank you for joining us today and welcome to SEG Evolve, what we're calling Fearless Explorer Fridays, where we're going to be inviting a series of industry speakers to come talk to us about key topics. Let me share my screen here. So we are streaming on YouTube and Facebook. And so I'm just going to make a few introductory comments here. So Jesus, is my screen good? Yeah, so we're going to have Fearless Explorer Fridays on a regular basis. It will be 9 a.m. Houston time, and it's brought to you by SEG, of course. It's SEG that established the Evolve program. Myself, Mr. Mike Forrest, who is here, and for those of you who don't know me, this is me over here, Alan Bertain, Mr. Mike Forrest in here, and always ably and enthusiastically supported by Jesus Nevares and Mario Bainas here, both geologists and recent graduates. For those of you that aren't familiar with Evolve, Evolve is basically a 6-month virtual internship that SEG offers to university teams, 5-person, usually multidisciplinary team. And so over 6 months, they get to work with a lot of real-world data and most importantly, interact with a whole series of highly experienced mentors. And that's a very rare opportunity these days. There are very few senior people available to contact and talk to in oil companies. And one key about Evolve, it is a collaborative project. The teams work together, they share information, and they also collaborate very closely with the senior mentors. So far, over the last, we kicked off actually in 2015. Over the last 3 years, we've kind of increased. And so most recently, we've put about 55 teams through these virtual internships. So we've had over 300 students from more than 40 countries. And you can see that on the map here. For those of you who aren't familiar, we are also offering Evolve Professional, which is essentially the same curriculum as Evolve, but that's for people in oil and service companies with 0 to, let's call it 10 years of experience. Anyway, we are going to have some upcoming talks here. Just to give you a sneak preview, Mr. Mike Forrest, very well known in the industry, affectionately called the father of bright spots by some, recipient of AAPG's highest honor, the Sidney Powers Memorial Medal. And he's going to give us a couple of talks on what he knows extremely well. So the keys to successful direct hydrocarbon detection, that's going to be on August 7th. And 2 weeks after, he's going to give a talk on best practices in AVO analysis. So stay tuned, we'll confirm all of this, but certainly we have a YouTube channel. Some of you are probably there right now, but take a look at that. And there are also links there to learn more about Evolve. And by the way, we also have a series of regional points of contact throughout the world, or ambassadors as we call them. And if you recognize any of these people, feel free to ask them about the student program, or if you have any questions about the professional program. So that's my quick introduction to Evolve for those of you who may be hearing about it for the first time. And so now we're shifting to Dr. John Karlo. Very happy to have him here today. So he's telling us that our next dry hole is probably going to be caused by seal. He has a long history in the industry, began his career at Shale. And I guess like Mr. Forrest, after he retired from Shell, he went on to do other things. So he worked at Maersk, Repsol, and I believe you were based in Madrid at Repsol some of the time.
Yeah.
And currently runs his own consulting company, John Karlo Geoscience. So with that, I will stop sharing, and Dr. Karlo, I will turn it over to you, and welcome.
Okay, well, thank you, and good morning or afternoon to everyone. And As Alan was saying, I've worked in industry for some 40 years. My interest and passion has always been in structural geology. And in that time, I have taught as well as coached working teams doing projects in various subjects in structural geology, including seal evaluation. And one of the things I learned from that is that there is a context to seal evaluation that professionals need to understand before they even start the evaluation. So what I'm talking about today, at the end of this presentation, you really still won't know how to do a seal evaluation. What I am going to try to do, though, is give you some information that you need to have, every geologist and geophysicist needs to understand before they even start. That's really the whole objective. So let me push just a couple of buttons. Okay, so what is everything that you should know that can you see my screen?
Actually, I don't believe you're sharing yet.
Okay, let me.
There should be the green button at the bottom there.
Yeah, maybe it just didn't click.
Yeah, maybe try again.
And now?
No, not at this moment. Well, here it comes. Yeah, there we go.
All right.
Yeah, very good. And I guess you can go to full presentation mode. Yeah, great.
Okay, great. Now we're on. So all right. So the subject is, what is everything every geologist and geophysicist need to understand about seal evaluation? So the first place to start is that this is the common perception of how risk is proportioned in a prospect evaluation. If you are looking around in the internet in illustrations, you will commonly see this figure, and you see in the figure what it is. Let me minimize that. What it is showing is that the perception is that most of the risk is in the depiction of the structure and whether or not you're really going to find the reservoir you predict. This image is common. This image is really no longer true because of 3D seismic, the widespread use of it, improvements in processing and resolution, seismic stratigraphy in understanding reservoir distribution, quantitative interpretation that allows us to actually measure reservoir properties remotely, structure and reservoir prediction can significantly be de-risked in a prospect evaluation. What the more correct image of where the risk is in a prospect evaluation shows up in modern lookback studies. There are numbers of these which have been done. I just grabbed one of them. This by Schlumberger, and is a survey that looked at responses from 20 different companies. And you can see how different the image is that you get here compared to that previous illustration. That here, trap and reservoir are caught, failure to properly image the trap or to understand the reservoir distribution results in the dry hole only about 25% of the time. The primary cause of failure is to improperly evaluate the seal. That is the cause of the dry holes almost half of the time. So this is one of the reasons for really focusing in an evaluation on understanding the seal. Now, having said this, there's another reason why this morning to focus on seal. And in that in my career for about the last 10 years, I was doing quality assurance work. The way this works in industry is that for the most part, senior management never will look at your technical work. What they're going to do is they're going to put their faith in you, in your team, and in work processes to be sure that they're being delivered the correct results. This, because I worked in this, I got to see over people's shoulders what they were doing in their evaluations. And what I saw was that quite often the SEAL assessment was really superficial, so superficial as to being meaningless. And the impact of this is that the numbers, the risk assessments, the volumes that were being delivered to upper management, which formed the basis of making drilling decisions, that quite often these were bad numbers. And there has been more than one oil company which has foundered and gone bankrupt because their portfolio was not delivering on its promises. So this is the second reason to focus, that seals are the leading cause of dry holes, and to a very large extent, the seal assessments being done are poor or bad. Now, why is that? There are a number of reasons. One of the most common reasons is an issue in workflow. It's very common that you're assigned a project, you're given a 3D data set. The first thing you do is load it into your workstation and you start working the seismic data. You have available these days fantastic tools for mapping, fantastic tools for amplitude analysis, for qualitative interpretation and reservoir prediction. And what often happens is that 99% of the time spent in the project is spent on the seismic interpretation, and everything else is done quickly at the last minute, the night before the big presentation of the work. And therefore the amount of time spent on the seal evaluation is just not comparable to the importance it is that you do it correctly. So this is the first problem. Now there is a second problem, and that is that if you go back to that first illustration I used, which showed how people perceive the risk in the prospect, the proportion, seal was not considered normally to be a high risk. So historically, because people didn't think seal was that much of a risk, historically companies have not been collecting data on seal properties. So whatever prospect, whatever play you are working on, quite likely you won't find that there is any data for seal properties for your play. And of course, how do you evaluate something when you don't have any data? So this is the second major problem. Beyond that, then, there's a problem basically with the state of the art. And what you find is that there is when you delve into literature, you would discover that there's very little consensus within the industry about seal phenomenon, about properties, about what it is you have to evaluate, and likewise how you go about evaluating it. To give you an example of this, this is comments that I've drawn out of the literature from workers at Exxon and from workers at Shale, both of which were looking at the fault gouge. which the fault gouge is the ground up rock on the fault plane, which gets created, during slip on the fault. And the question was, does this gouge actually act as a seal? Workers from Exxon would say, well, yeah, it can, but not very commonly, not very often. At Shale, they would say, oh yeah, this happens very frequently. We see sand on sand juxtaposition, which should cause leak, and we don't see leak across the fault. Therefore, the gouge must be the seal. Exxon would say, yeah, well, it does happen, but it's not predictable. You can't really do much with this. Shale, on the other hand, would say that's not true. There are a number of trends which are recognized and give you means of evaluating this. Exxon would say, no, I don't believe this. Most of the examples that you are pointing to are simply bad seismic interpretations, and if you interpret it correctly, you'll see that these examples that you're putting forward where you think the fault is sealing, really that's not what's happening. Shale would say, nope, that's not true. We researched this and we've worked these examples ourselves in great detail, and we know that this phenomenon exists. Exxon would say, well, no, okay, it does exist, but even when it does work, it's not very important. It doesn't really add much to the prospect volume. Shale would say that's not true. It really gives you the upside in the prospect. And at the end, both Exxon would say, well, my conclusions are based on my empirical studies. Shale would say the same thing. So when you're faced with this, and you're faced with a lack of consensus, how do you go forward? Another problem, which is illustrated in this, is this diagram, again, is looking at the behavior of fault gouge. And on the left, the y-axis, it's plotting what is the expected shale or clay content of the fault gouge. On the x-axis, these are the names of different fields and reservoirs within those fields within the North Sea. Looking at these examples, what this illustration is showing is that when the amount of clay on the fault plane is less than about 20%, you can pretty much guarantee that there is no seal. Between 20 and 40%, sometimes it seals, sometimes it doesn't. And when it's above 40%, you can pretty much guarantee, yes, that the fault gouge will be a seal. Now, this illustration is probably the most commonly cited illustration in all of structural geology. And it is cited as the calibration for what is the clay content of gouge, which acts as a seal. Now, when you actually look at what this is, and you can see the text lettering says this is based on only fields in the North Sea. It's looking at 13 fields, but in different plays. So you're mixing apples and oranges. And even in that, you're only looking at 29 traps, 29, fault juxtapositions. So it doesn't take much to conclude that statistically, this just isn't really valid. This is really statistically very weak. And it's only in the North Sea. So if I'm working in the Gulf of Mexico, I'm working in the Middle East, I'm working in Indonesia, how could it be that this is the illustration which is referenced? Well, quite simply, because this is the only published calibration that you will find in the literature on what is the clay content you need on the fault gouge to have a seal. And this illustrates a further problem in seal evaluation, that it is actually a very, very poorly documented subject. If you go into literature, you will find hundreds and hundreds, maybe thousands of papers on seal evaluation. But when you dig down, you find quite commonly that major concepts are documented in only 1 or 2 published studies, and they're all very local, and you just don't really have a global database that you can rely on. So in then summary, what you will find before you even start is that there is likely to be no data relative to your play. It is going to be very confusing which schools of thought you really should follow. And quite likely, you're going to be forced to extrapolate about your play from published sources, which you know have little or actually nothing to do with your play. The bottom line, which leads to poorly done evaluations, is that the evaluators often really just don't know what to do. And the cynical would ask, if the foundations of seal evaluation are so poor, is it actually really meaningful to do an evaluation in the first place? So for this, then, I'm going to delve a little bit then into what is the kind of philosophy that you have to carry forward in doing an evaluation. Because at the end of the day, you have to evaluate it. You know, in order to really carry your prospect forward, you have to examine the trap, the reservoir, the seal, the charge, and you have to assign quantitatively a value to the probability that the trap is as you've mapped it, that the reservoir is going to be present as predicted, that the seal is going to work, and that the structure indeed has received charge. And because the total probability for your prospect is the multiplication of those, it's very sensitive to the numbers you assign. And you have to deliver this. You just, there's no other choices. So again, so philosophically, how do you approach this? Well, anybody who's worked with me knows these quotes because I use them often. And all models are wrong, but some are useful. And further, how wrong does it have to be to not be useful? Having a wrong model that gives you meaningful information or a deeper insight into your structure, to your prospect, is still a good evaluation. We will have to accept that we're not going to be able to assign a really definite, clear answers, but we're going to be able to do a better job than otherwise would be the case. Now, one of the trends which is currently happening in seal evaluation is getting very involved in augmented tools like Brittle, where you can do an evaluation. It's delving a lot into details to an extent maybe which is going over the top, because the foundations of seal evaluation are weak, because it faces the challenges I've talked about to this point. One piece of advice is try to keep it simple. Make it as simple as possible, as fit for purpose as possible, and do not over-science it. So with all that, then, what do you do? How do you proceed? Where you're going to start in your evaluation? Well, there are 2 routes. As I said, there probably is little or no data about your play. So the first thing you could do is try to collect the play-specific data. Or, given circumstances, you may decide that that is not feasible, and you're going to have to stick with global analogs. Well, this is an example of some play-specific data. On the left illustration, on the y-axis is column height. On the x-axis is depth. Each dot represents a field, and these are column heights in those fields. You can see that this is an application of the kind of philosophy I've been talking about, that if your prospect was at 3 kilometers depth, empirically, it could have any kind of column height within that range. But the data suggests that there is an upward limit, a maximum column height, which is sustainable. And so this is an example of where you're not getting a complete analysis of the column height, but you are getting some useful information. Knowing what the maximum is certainly useful. The right illustration is very similar. This is pressure contrast across the fault, but think of it as column height. This is, again, clay content of the fault gouge. Each one of these dots represents an analysis of pressure differences across a fault. And again, this is suggesting that there is a maximum column height which is possible for a particular clay content. Now, if you don't go that route, where you're trying to collect data specific to your play, obviously, then you're off to the library. And you have a number of sources that you can go look into. Obviously, it is scouring the literature about your play, about properties, about mechanisms, about how to evaluate them. If you're lucky, there may already be existing in-house studies which have been done. And in addition to that, at the bigger companies, there has been for, I don't know, at least the last 10, maybe even 20 years, a research consortium called Rock Deformation Research in Leeds in the UK. And a lot of the work product of rock deformation research has recently been bought by Schlumberger and has been incorporated into their Brittle software. And rock deformation research, the way that worked, is that a company would, to join the consortium, have to pay some money, and it would have to collect some seal samples for analyses, turn those samples over to the lab in Leeds, which would then collect the data. And rock deformation research then would harvest all the results and share all the results amongst all the participant companies. So companies such as Shell, BP, and others in their files would have large amounts of data from different global settings, which could be used in an evaluation. So a second then cornerstone of how you approach it is to consider what are the ways that seal may fail. And there are basically 6 phenomenon that you would be paying attention to, 3 relative to top seal, 3 relative to fault seal. The good news is that for the most part, for your particular play, you really would only end up having to analyze one of these, not all of these. For top seal, it is capillary seal, the brittle failure of top seals, or the ductile failure of top seals. In fault seal, we have to look at cross-fault juxtaposition, the potential formation of shale drapes, and then lastly, fault gouge. And I'll step very briefly through each one of these. So what is the main mechanism of top seal is what is known as a capillary seal or a membrane seal. And probably all of you are familiar with the phenomenon of surface tension. And there is between the water wet top seal and the hydrocarbon wet reservoir, between the hydrocarbon and the water, there is surface tension. And in order for the hydrocarbon to leak through the top seal, it has to penetrate into the pore space of the seal. And you have to overcome that surface tension. The amount of the surface tension will be controlled by the size of the pore space that it has to get into, and of course by what kind of hydrocarbon, gas, oil, and the composition of the oil within your reservoir. Now I want to illustrate this, so let me push a few buttons for a second. And this is a little video and illustrates the phenomenon of top seal. So let me pause it here and explain what you're looking at. First of all, this is an aquarium. And the aquarium is filled with water. And in the aquarium, you can see supported by a couple of rocks, there is a pasta strainer or a rice strainer. And you can see that the bubble machine of the aquarium is feeding air from underneath into the pasta strainer. The pasta strainer obviously has great, porosity. It has infinite permeability. Nevertheless, what you can see here is that we have a gas cap of air which is caught within the pasta strainer. And what is maintaining this is the surface tension that has to be exceeded in order for the air to be able to enter the porosity of the pasta strainer and then leak out of the prospect or out of the trap. So let me go back here for a second. The amount of pressure, the force that is necessary for the top seal to leak is the capillary pressure. This is related to the column height. It is a function of the interfacial tension, which is the surface tension, the pore space, and of course the interfacial tension relates to the composition. Quite likely you won't have any laboratory measurements for this in your prospect, unless you may have to appeal to global analogs. You may be lucky and have access to the rock deformation research data. You may have to infer the properties from things that you can measure. Here, we are correlating capillary entry pressure with the clay content of the top seal or with the bulk density of the top seal. Both of these will relate to pore size. You are quite likely not really to have any data about the interfacial tension for the hydrocarbon which is in your reservoir, and we'll have to use some kind of a global calibration. If you do, you know that there's quite likely that it's going to be wrong, that your interfacial tension will be different because it is very specific to the composition of the hydrocarbon. But you come back to the philosophy that says, okay, I know this model is going to be wrong. All models are wrong. But do I get any useful information out of doing this evaluation? Does it allow me to narrow the range? Does it allow me to set limits? Does it allow me to define maximum column heights? Does it give me something still which is useful and therefore is better than doing no evaluation at all? It's also important to understand what happens when top seal fails, and this is quite often misunderstood. So let's go back to the video. We're building column height. The capillary pressure is increasing. Now let's go back and look at that again just for a second. So you saw that we got to a column height where we now have enough pressure to overcome the interfacial tension. The top seal has blown. We catastrophically lost most of our column, but notice that we didn't lose it all, that there is still column now left in the trap. And if there's still charge migrating through the system, at that point, you can begin refilling the trap. So an important thing to understand then about top seal is that, as shown here, the same thing here is the pasta strainer. We fill the trap, we get to a maximum, we can lose a lot of the content of the trap, but we're left with a residual column, so the trap is never fully empty. Okay, moving on. What then is the second failure mechanism one might encounter for the top seal? It is brittle failure of the top seal. This example here is from the Barents in the Norwegian Arctic, call it North Sea. This is the water bottom. You can see there is an angular unconformity below which you can see the structure. These rocks have been down, were more deeply buried, they were compacted, then there was basin inversion and brought shallower to the surface, which is when this angular unconformity then was cut. These rocks then are harder, more dense, more brittle than they would normally be for this depth of burial. The other thing which you can see is here is a flat spot. There is an accumulation here, and that the flat spot seems to correlate with the contact with the fault zone at either end. And indeed, what is happening here, if you zoom in, is to see that the fault zone is actually rubble. It's a breccia, because the rocks are brittle. They just break up, and instead of being then a potential seal, the fault zone itself is a migration path which controls column height. If you think of what do we mean by brittleness, you know, or hope you know, that glass and steel actually have exactly the same hardness. Um, what is different about it is how much bending the material can take before it breaks. That's what we mean by brittleness. How are you going to measure, though, for your prospect, the brittleness of the top seal? Well, remotely you cannot. There is no information from well logs nor from seismic itself, which directly will measure brittleness. In order to have to evaluate it, you're going to have to infer the brittle behavior from things that you can mention, things like the density, Poisson's ratio versus Young's modulus, elastic impedance. These things will have a relationship to brittleness, will indicate whether or not your top seal is brittle and potentially how brittle it is, which allows you to state whether there is or is not a risk of brittle failure. Again, it's a case of, you know that the model is wrong, you're not actually measuring the brittleness, but you still can get from it some useful information. The last way that top seal can fail is in hydrofracture. You can think of this as a kind of fracture of a ductile top seal, even though that sounds a little bit contradictory. I scoured the Google trying to find an image of an outcrop of what does this actually look like, and this is the one I came up with. This would then what a seal would look like, which has undergone hydrofracture, and you can see all these little sand stringers which have basically blown through the top seal. The way this happens is here we have a plot of depth versus pressure. This line represents the pressure within the water column, both within the seal and the reservoir. With increasing geopressure, this line would move further and further to the right. This line represents what the pressure would be in the reservoir owing to the addition of a hydrocarbon column. And this line would represent the failure line. At what pressure would our top seal fail? The separation of the water pressure from the failure pressure is called the aquifer seal capacity. And there are calibrations, empirical calibrations, in this case in the North Sea, for at what kind of pressure difference do we see seal, do we see a mix of seal or not seal, and do we see failure? This is similar to, using this is similar to the illustration I showed for calibrating clay content in the gouge versus the chance of that fault sealing. It's not your basin. It's based on limited data. It's based on a setting different than yours, but this is the only calibration that you have. So you're going to go and use it with the understanding that, again, this model is wrong for you. All models are wrong. Is it giving you useful information? For your prospect, the critical factor may not be the top seal, but may be the fault seal. The most basic and simple consideration is what is the juxtaposition. In this case, obviously, reservoir A is juxtaposed against shale. You think it's going to seal. Reservoir B is juxtaposed for most of its thickness against shale, but the bottom of the reservoir is juxtaposed against the top down thrown, so at this point may leak and control the column height. And reservoir C, the top of it is juxtaposed against sands across the fault, and this is likely to leak, and therefore likely to be no accumulation. There are tools which allow you to do this. The simplest is called an Allen diagram, where you make a graphical representation of the fault plane. You draw on that representation the stratigraphy of the upthrown side. You draw the literally draw the stratigraphy of the downthrown side and inspect it for potential leaks. And then just stop and think about then how that potential leak controls potential column heights within your prospect. There's another tool called the triangle diagram, which is used for quick scoping. The way it is done is you take your stratigraphy, you make a projection horizontally of that stratigraphy, and you make a projection on a 45-degree slant in order to use it in this graph. And the way to think about it is, if I want to know for how much throw on the fault does it take for this sand to juxtapose against that sand, I simply follow down the graph and I say, okay, the bottom of this reservoir juxtapose the top of that sand. My fault throw is anything between beginning at about 55 meters. The middle of this sand will juxtapose against the middle of that sand when my fault throw is about 100 meters. So I can inspect my faults at 100 meters to see, do I have 100 meters of throw anywhere? Do I have 50 meters of throw anywhere on this fault? And what is then the implication? So there are some tools that one could use. A second phenomenon that you would have to pay attention to in some cases is what is known as a shale drape. And you can see on the left illustration, there's an outcrop example of this kind of thing. The way this forms is when we have a sandwich of brittle and ductile beds, and we begin to develop faulting. You can see that we get fractures within the brittle beds, but of course not within the ductile beds. These line up in an en echelon fashion. So we actually have a monoclinal fold of the ductile unit separating the two brittle fractures. As the fault develops and continues extending, you can see in this lab experiment what happens. We smear that out, and we end up developing, as shown again in this outcrop example, a continuous layer of shale along the fault plane. There are, again, a few, not many, but a few published calibrations of this. And what kind of fault throw do you get smearing this out? And at what point have you smeared it so far that you develop holes in the monoclinal fold and you will allow leaks to happen? Again, it's the same philosophy. You know that these calibrations are not in your basin, they're not in your play, but these are the only calibrations you will find. And is it still potentially telling you something useful? The last one to talk about is what happens then about the fault gouge. Here's an exact outcrop example. You can see the ground up rock a few centimeters thick along the fault plane. And this is evaluated using a concept called the shale gouge ratio, which is a really very, very simplistic idea. And for any point on the fault plane, you simply look at what is the stratigraphy which has been displaced past that point. You will add up what is the shale content, the thickness of the shale within that stratigraphic section, and you will divide it by the throw, and you get a number. And that number is anywhere between 0 and 1, or you could express it as 0 and 100%. Now, that is used as a proxy for how much shale, what is the clay content of the fault plane. Quite realistically, this is a very, very simplistic approach. When you look at real examples, as you can see here, in reality, the gouge is not very homogeneous. It's not uniform. To think that my shale gouge ratio number is actually a real depiction of what's going on the fault plane clearly is not true. It's a model, but again, all models are wrong. So why do we use this one? The basis is purely empirical. This is the results of a look-back study that was done by Shale. Each point on this plot represents a reservoir with a sand-on-sand juxtaposition. You can see that I don't even know how many there are in this data set, but you can see it's a huge number. On this axis, think of this as column height. On this axis, this is the shale gouge ratio, your very, very simplistic guess as to how much clay is on the fault plane. And you can see then for any particular guess as to clay content, we see a distribution of column heights. But again, what comes out of this is seems to be a clear maximum. And this is useful information. Now, to use it, you need calibration. And again, we're in the same circumstances I've shown before. There is only one published calibration, and this is done by the crew at Baddeley's in the UK. Graham Yielding is the author who mostly publishes it. You can see here we have pressure difference, which is we can translate into column height. Shale gouge ratio, again, each one of these dots represents a point on a fault plane. And in the right-hand illustration, they've broken it out by depth, and they give you 3 different calibrations for shallow, intermediate, and deep faults, and what is the maximum column height you can develop in those settings. There are other calibrations done by Rock Deformation Research, and as I have said, those are incorporated into the Brittle software. And but if you don't have access to that, then the only thing you find in the literature is the preceding illustration by Graham Yielding. Okay, that's is a very, very quick treatment of, before you even start thinking about seal, the things that I think one needs to know, one needs to understand before you begin approaching it. I commented before, there are hundreds of papers, maybe thousands of papers talking about seal. If you as students want to learn more about the subject, I've picked a few things here. 3 basic papers. You can see 2 by Graham Yielding talking about seal evaluation. But then beyond that, making it maybe a little more entertaining, I picked some YouTube videos. One on capillary seal. It's made by students, so it's a little more fun maybe. But in any case, it talks about top seal, seal and migration, a lot of the basics about seal, and then the last one by Schlumberger, which is a very overall treatment which tells you more about how you go actually analyzing it. These references you can get via SEG Evolve, and will be forwarded to anybody who wants them. So thank you for allowing me to share my morning with you. And I don't know if we are able to answer questions or not.
Sure, we do have time, so maybe you can unshare your screen for now.
Okay.
Yeah.
Okay.
So anyway, we certainly, on behalf of SEG Evolve, certainly want to thank Dr. Karlo for being here, and I guess we'll try and give him a virtual round of applause here. Yeah, okay, I guess that's right. Yeah, in computers, you can put the little hands in there. So I think we'll open it up for questions. For those of you who are in the Zoom room, you can actually come live and ask your questions. And I believe, Jesus, that for those on YouTube and Facebook, they'll be able to text you in the chat there so that we can hear the question. So that's it. I had lots of questions myself, and I'll just kind of throw them out, and maybe you can address them later or whatever. But I mean, in some ways, I'm almost amazed how many wells actually core fault gouges, because obviously core points get selected usually to be in reservoirs. So
Yeah.
how does it even happen that we even have any cores on real wells in fault gouges?
It has to be on purpose, obviously. I was trying to stress that quite likely in your play you won't find any data at all, unless you belong in one of these consortiums or have through your company some access to this. Because the way the consortiums work then is that the company has to pay some money, and it has to supply the core. So, for instance, when I was at Maersk, we wanted to join the consortium, but we had to wait until we had a well going down, where then on purpose I could say, okay, now we have to core this fault plane because I have to have samples. They won't let me into the consortium unless I have samples to contribute. Now, once I have samples to contribute, now this opens the door and I have access to all the samples which have been collected by all the other companies. So based on that, within the industry, yeah, the data exists, and we do know about the properties of fault gouges, but you won't find much of that published. It's considered proprietary.
Okay, yeah, thank you for that. I guess the other question I had is more of a philosophical one. As you say, prospect evaluation, we're dealing in this nebulous world. And I often think of prospects where people say, well, here's the fault, and this is where the hydrocarbons are coming up. And then that same fault is the seal for the prospects. And I just wonder, what are your thoughts on that, having seen many of these seals all over the world and prospects?
Yes, well, I can tell you what the idea is, and so as I showed with the little video on top seal, that you can blow the top seal, but you don't actually lose everything in the trap. So for instance, I work Sakhalin, which has a number of these mega oil fields. Every single one of them has a huge gas cloud sitting on top of it. So on the one hand, yeah, the trap has leaked, but yet everyone has a major accumulation. So quite often there's in the conference room a question of, well, does a seal leak or fail? Does a trap or fail? And the answer to that is actually yes, it does both. Well, the fault gouge, I was talking about, okay, our guess is as to how clayey, how clay rich is this gouge. which is the same question, is how clay rich is your top seal? Because again, that controls the grain size, controls the capillary entry pressure. So the fault seal, the gouge, also has a capillary entry pressure. The place where you see this really in action is at the production scale. That at the geologic scale, it doesn't make any difference how permeable it is, because you have millions of years of time to migrate through that permeability. At the production scale, permeability now becomes a real question. And what you will see is there are faults which on the geologic scale don't trap. But once you start producing the field, all of a sudden now that fault is a trap. Because it has a clay content, it has a grain size, it has a low permeability, and you, in production scale, you can't migrate through it fast enough. So yeah, so the fault both can trap and seal depending on circumstances.
Okay, well, let's see now. Do any of the students, and maybe we should ask you to raise that digital hand if you have a question so we can be somewhat organized on the Zoom. If you do want to ask a question, could you raise that digital hand, which is what, under reactions, I think, is the symbol in the lower part. Okay. So we have Mr. Alex Biolar. He's on the SEG Foundation. He's a structural geologist who spent a lot of time out in the field, I think in the Marathon area in West Texas. So over to you.
Hi, John. Thanks for the talk. It was really informative. I had a question regarding the types of clay. You know, we kind of say the clay content is the main driver, but is there any differentiation or work done on the types of clay, whether it's oolitic or smectitic, that affects it?
Yeah, there are basins where you have the illite smectite transition happening, and this is known from some of the northern basins in Australia, for instance, and where the same top seal has different properties based on the diagenesis of the clays, and where then in different parts of the basin, the top seal potential is different. So on the one hand, it is known as a phenomenon. But again, if you ask me, in the Gulf of Mexico, do we have any handle on this? In the Gulf of Mexico, my answer would be no. At least I am not aware of any published work on that subject. So there may be such place-specific work.
Great, thank you.
Okay, let's see. I'm looking in the chat here with, let's see. So one question is, three questions. Let's see. A question about the influence on seal properties of wax. Actually, you may be able to see these if you click on your chat button.
Okay.
Question about the influence on seal properties on wax formation in producing wells. Then there's a question, could basin analysis be helpful to determine leads, which I guess are likely to have seals or not?
Well, yeah, certainly one of the things which should be done is that the play-based exploration has become industry standard. And you wouldn't ever think of walking into the conference room and talk about your reservoir evaluation without having maps showing the distribution of porosity, permeability, thickness of the reservoir, facies. you would have it all mapped out. Obviously, the same philosophy should be applied to seal. And you have a regional shale that within your basin, there are differences in thickness, there are differences in facies, there are differences in clay content, maybe differences based on diagenesis in clay composition. You ideally would again have all this mapped out as a foundation then for what is your conclusion about seal in your prospect. So that kind of basin analysis certainly should be a routine part of the evaluation. Quite often it is not, because it's very time consuming. A lot of the data is not easy to come by. You have to really have a focused effort to collect that data. And if you don't build this into your work program, I showed the seesaw example of, how much of the workflow is based on interpretation and how much is everything else. If you don't build this into your workflow, you just don't get it done.
I think someone has a question here about a particular paper that was published by Milkoff, 2015 Earth Science Reviews. And I guess he proposes certain methods for evaluating top and lateral seals. And is that something you've ever tried, I guess, is the question.
Yes, I have tried it. I applaud Dr. Milkoff on his philosophy, and that the idea of risk tables is a great idea. It is the way that risking should be done. If you get a bunch of people around a conference table and say, what do you think the risk is? And people have to assign numbers, you find that there's a large amount of scatter. And you just don't know how good the numbers are or are not. And even if you take experts and you ask them, what do you think the risk is, you find a large amount of scatter. Research has shown, though, that if you actually put it in words, is it likely, very likely, unlikely? Actually, when you put it in words and not numbers, we have less range, less scatter, and much quicker agreement about our assessment. And what Milkoff is doing in the risk table approach is then trying to define, give some definitions on how to use this and how to use words to get to a better risk assessment, a better quantification. Now, in terms of then the tables that he has put together, what he's published, this was really his first shot at it. And not to take anything away, I'm not so crazy about his seal tables as I am about some of his others. And this is where, for me to use it, I would polish those tables down a little bit. But as far as an approach, I think philosophically it's a great approach. And when I was at Repsol, I actually built a set of risk tables to use as a company standard. So it can be done. I think his are a reasonable starting point. And certainly, again, you come back to all models are wrong, but is the model useful? If you don't have anything else and you want, where do I start? Well, start with his risk tables.
Okay, thank you. I see there's another question here about how we explain sand on sand juxtaposition in a sealing, I guess, situation. Is it due to shale smearing, or can it be due to cataclasis?
Okay, you're going to get two different answers. First, the whole approach of shale gouge ratio is based purely on empiricism. And I will share with you when I was a young punk doing my master's study in Arkansas, was at an outcrop with an older geologist and was irritating him a bit on how do we interpret what we're seeing. And one of the things he said to me, boy, I don't need to explain it as long as I can photograph it. So if you ask me what is really happening in the fault gouge, I mean, there are studies, there is work has been done, research has been done. What's really happening in the fault gouge? Is it how homogeneous is it? What is really the mechanism for generating the fault gouge? Because so few of these have actually in the subsurface have really been cored. There's a lot of unanswered questions. The approach, though, is based on empiricism. You look at that Shale Lookback study and you say, okay, even if I don't really understand all the mechanisms involved, what I'm gaining from it is an understanding of what is the maximum column height I can trap. And that's purely empirical. Now, in terms of what is the mechanism, for cataclasis, cataclasis is indeed when you have, you're grinding up the rock and you're creating a more sand-like gouge. That will only happen when the clay content of the rock originally is less than about 15%. When the clay content of the rock is greater than 15%, then the clay grains start acting as a kind of a lubricant within the gouge, and you begin to get slip, and you don't get that kind of grinding anymore. So once you get beyond about 20% clay, now the phenomenon, instead of grinding to create the gouge, becomes more of a mixing phenomenon to get the gouge. And you sort of think, well, okay, the more displacement I get, maybe the more mixing I get, but that really is not tightly controlled by either empirical or experimental work.
Okay, thank you. Let's see. I don't think I see any other questions in the chat, and so how about some of the individuals in the Zoom room?
Can I ask one, Alan? Mike?
Yeah.
Yeah, John, talk about the amplitudes, how and DHIs, how that fits in all this.
Well, it does require some thought. So to start off with, let's consider what happens with a top seal. And I've already shown that you can have a top seal, and the phenomenon is a kind of hysteresis. We fill the trap, we get to a certain column height where the buoyancy pressure is enough to overcome the capillary pressure. We can blow through the top seal, but we only blow part of the column. It will then reseal, and we could refill it. So you can then have amplitudes. You could have a flat spot, for instance, which is showing you the filled trap. You could also have an amplitude which is based on the residual. You know, it's basically a paleo flat spot where we can blow the part of the trap. We will leave residual gas, for instance, behind our 10% fizz gas. We still see the flat spot, we still see the amplitude, but the trap has been blown.
That does happen. We have several cases. I've seen several cases of that.
Yeah.
Okay, let's see. Anybody else have any questions from the Zoom room, or I guess from the YouTube or the Facebook?
Yeah. Well, let me go back for a minute to Mike's question. One of the things which is a flag to look for
Oh, sorry.
is that this of paleo flat spots. One of the things to look for is when you think you see a flat spot on seismic, is it really horizontal? And one of the big red flags is when you see a flat spot which actually isn't really horizontal, that there's a likelihood you are looking at a blown trap or a partially blown trap. You don't have a full column height anymore. And I do know of a few examples where actually you see what clearly looks like a flat spot, except that when you actually put it in depth, you find that it has a dip to it. And what is shown is that this was a flat spot at an earlier stage of the structural evaluation. You blew part of the column and you rotated it later. And I've seen those on seismic.
Let's see. Yeah. Okay, so I think I don't apparently no more questions from the YouTube or Facebook channels. Doesn't look like we have any further questions here. So I think John will thank you once again for spending the time here with the students. As you heard, we've got some references for you that we'll circulate and make available. So thank you again for participating, and I'm going to sign off with one slide here, but let's give you another round of applause as best we can. So I'm going to share my screen. Let me get my slides here to close this out. So what we will say, by the way, is that for the Evolve students, we now move to office hours, so you're welcome to stay. We will close out on the Facebook shortly. Let's see, where did my window go here?
Dr. John Karlo, I also want to say thank you, and that there were a lot of thank yous on the live stream.
Well, thank you, Mario.
Yeah. Okay, let's go back to this. Oh. Let me see, full screen. And I'm going to try and share here. Okay. Are you seeing the screen, Mario or Jesus?
Yes, perfect.
So we're going to close out here. So, you know, SEG Evolve is about developing the fearless explorers of the future. We're fortunate in many ways that this was always set up as a virtual internship. So we've been practicing this for quite some time. And by coincidence, somebody came here. So in spite of COVID, you know, we are unstoppable. And that's the way we plan to be. So with that, I think we'll close it on the Facebook and the YouTube, and see you next time. And now we'll revert to the Zoom room for the students.